Thank you everyone for joining DSC 102, the industry guest lectures. First, we have Shreya Shankar from, well, technically she's on break right now. She was at Google before this, and then she was the first ML engineer at Viaduct AI before that. And Shreya has been posting a lot about her experiences, technical and other non-technical, about ML engineering, this new emerging professional field, combining data infrastructure systems and DevOps and ML methods and algorithmics. And she is very active on Twitter, like me. And so it's great to connect with Shreya and have her visit this class to speak to the students about her experiences with debugging machine learning in production. So Shreya, your screen has gone black. I don't know what's happening. Okay, now it's
Okay.
good. Please take it forward. Protocol for the talk. Please raise your hand if you have a question. Shreya, would you like questions at the end, or are you okay with taking questions in between?
No, in between is good, ideal.
Okay, so folks, please raise your hand and then I will monitor for raised hands, and feel free to unmute yourself and ask or put the question in the chat. Great, take it. The floor is yours, Shreya. Go ahead.
Thanks. How long do I have?
Oh, so you have an hour. The class goes on till 12:20, but yeah, typically like 50 minutes, 10 minutes Q&A.
Okay, sweet. Yeah, thank you so much for having me. I'm really excited to be here. I'm going to talk about just ML in production, generally what happens after you train and evaluate a model and then deploy it, what happens after that. Super unexplored area in research, which makes it really exciting. But this is what industry is working on every second of the day. So let's get started. Yeah, so I guess to go through this talk as quickly as I can. I might not get through everything. I'll talk a little about myself, just an overview of the production ML pipelines that I've seen, go into a simple case study of like what happens post-deployment and some challenges around that, which could motivate some areas for future work. And please ask questions anytime throughout this talk. So a little bit about my background. I did my undergrad and master's at Stanford in systems and AI. And I also did research in adversarial machine learning and deep learning robustness, both at Stanford and at Google Brain. And I, after graduation, went to become the first ML engineer at an applied startup. I don't know why this is unfortunately refreshing every time.
Something wrong, Shreya? So the screen is visible for us just fine.
Okay. Yeah, it just flashes every time I switch slides. So I guess it's fine. We can work with it. So at my company, I guess my workflow is a lot different from when I was doing research when I was in school. So for example, I worked with terabytes of time series data. I helped build infrastructure for large scale ML and data, and kind of my responsibilities were all over the place, from recruiting to engineering, ML, data science, product, and more. And my interests kind of evolved from both from school and research to industry stuff. So in an academic setting, I trained a lot of models, like you can imagine, final project classes, ML research with their like 3 or 4 conference deadlines every year. I trained lots and lots of models, and I cared deeply about deep learning robustness as an academic field. But whenever I got into industry, I realized that I was training very few models, or I wanted to train very few models, but do lots of inference on those models and really focus on how do we leverage these models to actually get us some sort of value. So maybe in academia, I cared a lot about like fairness or generalizability to unknown distributions, security against like adversarial attacks. But then in industry, really it was as simple as like, if I deployed XGBoost model, what happens beyond the test set? And that's the motivation really for this talk. The depressing truth about ML, I think many of you may know, but essentially, like, there's a lot of articles out there that talk about how very few data science projects actually make it to production. And essentially, maybe one of the reasons why is that data in the real world might not necessarily be clean and balanced, like canonical benchmark data sets, for example, ImageNet, and so forth. The data in the quote unquote real world is always changing. So for example, like in an extreme case, COVID hits and now all of a sudden the kind of data that your company is receiving kind of all over the place. And I think the bottom line is that showing high performance on a fixed train and validation set is not necessarily consistent high. It does not necessarily mean you will have consistent high performance when that model is deployed. And maybe this is just something that you take for granted now, but I can kind of show you an example through a case study later on of how performance could just drop. Okay. Next. Cool. So for today, I won't really be talking about ML-wise, like how to do better data science or improve model performance on a validation or test set. Can you still hear me?
Yes, Shreya, we can hear you.
Okay, perfect. I think that's my earphones went out. So I won't be talking about that or feature engineering, but I will be talking about kind of like an overview of production ML pipelines. What's the both people perspective of this kind of how do different people collaborate to build this kind of ML? And then also technically, like what are the different components of a production ML pipeline? And hopefully this motivates this whole field of MLOps as a discipline. All right, so diving into the production ML pipeline overview, I think at a high level, I'll talk about both the people overview and the technical overview and the different kinds of people. So for example, like product managers or biz dev or engineers, not super thought about as much in ML academia, but then the technical tools may be something that people in academia or school think a lot about. So going over the people overview, I think something that I realized when going into industry is that there's lots of stakeholders in an ML project and many technical dependencies. And these stakeholders don't necessarily have the same like technical skill sets or speak the same language. Where it was very different from when I was working on a research project or a final project where like everybody is very deeply familiar with the kind of like modeling going on, either advises it or works on it. The other thing with applied ML that I've seen is that like domain experts are super key. I think people also call them subject matter experts, but essentially I was building ML for OEMs or car companies to help predict whatever components of these cars. I don't know anything about cars. It never worked whenever I just all of the data in a deep learning model. So really the idea was how do we kind of leverage the fact that some people do know about how broken crankshafts work, I don't know, or something like that, and turn those into features, encode them, productionize them, and so forth. The other thing that really was of concern when I was in industry is that, especially in a startup, but I think this is across the board, the data changes and also the business requirements might change. So for example, maybe a client might say they really care about recall 1 month, and then the next month, actually their problem has changed to a precision problem. Whereas kind of when I was in academia, it was clear to me what exactly the metric was, what exactly it had to be, and I don't know, incrementally improving on something that already existed in the literature. The other thing about, I think, industry ML is that modeling really is just one part of the pipeline, even from a people perspective. That's owned by maybe an ML practitioner, a data scientist, but it's treated as software, right? And if you've ever worked like in software industry, people will build software and tons of people will maintain that software. Even if the original owner left that team or something, other people have to quickly onboard and know how to maintain it. And if you've, I don't know, built an ML pipeline, if the models are extremely complex, it can be extremely hard to onboard someone else onto this. And then if people have issues or bugs, right, like say, oh, this ML model may have misclassified this example. Who do you relay that feedback to? Is it the PM? Is it the engineer? Is it the QA person? Is it the actual data scientist who might be on a different project? All of these questions are still super unanswered in industry from like a collaboration perspective. And then here's like this diagram that I found in some book that I read. And I think this diagram really does justice of how complicated all of these like feedback loops from a people perspective can be, like from data scientists to the subject matter experts to engineers who are all trying to work with each other, but not all of them have the same skill sets. So it can really be quite challenging, if not more complicated, honestly, than this. I'll pause here if people have any questions.
Okay, folks, any questions? Feel free to raise your hand or enter it onto the chat. Okay, we have a question from Evan. Evan, go for it.
Yeah, so it's kind of like a general question. So like what's like the expected accuracy of like AI models in like production? So let's say like the model needs to predict what type of cat it is. Like, would you say like over like 99.9 is good, or like even that is like too low, or like yeah, or I guess
Yeah.
I'm sure it's different for every model, but yeah.
Yeah, it's different for every project. And one thing that I spent 8 months at my company just like trying to eke out as much performance as I could before realizing it doesn't matter unless somebody from biz dev tells me, hey, like this is how much the client is spending on, I don't know, fixing this part. And so minimum you need to get at least this percentage recall to save money, or to make it worth it. And I think that kind of calculation is not something people, or like I was ever used to doing, this kind of like, or like forecasting like what is valuable. It really required me sitting with the biz dev person like every day for a week and trying to exactly figure out how the client spends their money and what is the easiest way to apply machine learning that saves the most money, if that makes sense. And I think this is different for every team, which also makes it really hard for ML to scale.
Okay, all right, thank you.
Okay, Shreya, we also have a question on the chat from a student. What are your views on the separation between data scientists and ML engineers, architects? What are their differences in skills?
So data scientists, ML engineers, and what was the last one?
ML architects.
ML architects. I don't know what an ML architect is, but I can speak to maybe data scientists and ML engineers. I think right now ML engineer is a very catch-all term for people who do both data science and software engineering, because there's this discipline of taking like a PyTorch model or a scikit-learn model that some data scientists come up with after heavily iterating on a data set and kind of packaging that into something and deploying that on some Kubernetes pod or something that like, and monitoring that, right? Like being that kind of liaison for people who are using that model on a regular basis, and then the data scientists who are trying to actually improve on them. I don't know if this is how it will last in the future, just because I can say as an ML engineer, I literally did every single one of these blue rectangles, which may or may not scale again. But right now, I think there's a lot of low-hanging fruit and like open questions on really how you can seamlessly enable data scientists and engineers to collaborate.
Thank you. And we'll also cover this distinction with ML deployment and ML ops and stuff later in the class as well. So Shreya, you can continue. Thank you.
Okay, so going into more of a transitioning to the technical overview, right? Like first, I can tell you a little bit about the life cycle of an ML project that I kind of converged on after doing this multiple times. How do you kind of like have a bunch of stakeholders that work together, and what kind of flow do you go about? So maybe that was at first like get all the people in the room, figuring out what exactly the metric is. And one mistake that I really made in my first few projects was I got the data and I immediately spent 5 minutes cleaning it and trying to train a model on it. Whereas it wasn't clear to me what exactly, my bad. What exactly
Something wrong?
My notifications.
Okay.
Oh, maybe if you didn't see it then. Okay. it wasn't exactly clear to me what the metric was supposed to be for building a model and then kind of iterating on that, especially if the biz dev people or the clients kind of change that on you on a regular basis. It becomes really hard to kind of build something of value for them. So really aligning on the exact metric, maybe that's I want 70% recall, and that is the acceptance criteria that will deliver value, and we should deploy that. So making sure everybody exactly knows what that is and how that maps to some sort of monetary like ROI. Then as an ML engineer, I found it much simpler to really write all of the data pipelining and infrastructure around the ML model, like treat the model as an if statement, and then write all of the ETL, or I don't know, the data pipelining around this. So that way I could think just think only about IO, schema, and deployment, what would happen. Then it just became a simple act of like, okay, look at the data, clean it, try to get some signal out of it, feature engineering, build some models, substitute that in the if statement, see if that improves, I don't know, and then keep cycling on this. And once I was able to separate this, then technically it became much easier to kind of build some sort of framework for a bunch of data scientists to collaborate on different tasks. And I think Uber does a very good job of having good blog posts of what their kind of like technical data science infrastructure or technical like ML pipelining infrastructure is like. Everything from the data lake to actually serving the predictions, right? You want to standardize as much ETL or data processing as possible, put it in some sort of feature store, have a component that allows multiple data scientists to use the same features but work on different prediction tasks, and then deploy their models, serve the predictions, whatever. And furthermore, how do you separate the offline approach, which is like data scientists kind of looking at tables of data and building models, versus the online approach of you deploy a model and now like records come in a streaming fashion and you do need to serve predictions and then monitor the quality. Cool. And kind of this is really what we based kind of our infrastructure startup off of. And the key requirements that we had were really scalability and reproducibility. So how do we have multiple data scientists, like not just like 2 or 3, but maybe 10, 20, even more data scientists working on the system and then able to reproduce each other's workflows. And that requires like versioning a lot of data, models, and artifacts. Like you could imagine, how would you build software at a company if you didn't have Git? You need to have that for ML somehow, some CI/CD, but then ML is more than just code. It's the data, it's the models, it's the hyperparameters, it's the artifacts, like literally everything around this sort of training business, which can make it more complicated. Also the metrics, versioning them is important. I think one classic example of when I was working and I versioned the models, like model binaries, and that's about it. And then I had 2 model binaries sitting on my computer and I did not know the difference because obviously if you diff them, right, there's a difference in bytes, but like performance wise, was there a difference? I knew what data went into them, but at a high level, right, you want to easily be able to diff 2 artifacts or 2 models, and you really need all the information around that. Maybe that's the accuracy or recall.
Shreya, there's a
question.
Hand raised. Yes, Siddharth, go for it.
Wait, actually, how do you version it in like software wise or anything? Because for example, in Git, you can't upload that big models and stuff.
There's a great question. Well, how do you version? I mean, Git version software. Are you asking how do you version in?
Like how do you store it? I guess maybe, yeah.
Oh, in ML. Yeah, this is a great question. Different companies do this differently, and there's like 300 tools out there to version like every single one of these bullet points. I will say that our company relied a lot on MLflow, which is essentially like this database where you can like say like this is the kind of model architecture I have, and then these are all the different model binaries. I don't know that it produced, and then you can log various metadata, but you have to select the metadata. I think that's the hard part with MLflow. You have to know exactly what you want to log, and like maybe that does all of the data management for you. But if you don't fundamentally know in the beginning what you want to log, then it's hard to use. Another thing that we did that was helpful was we we used Airflow, which is just in general for all workflow scheduling. So if I wanted to train a model, like it would be an Airflow job. And that links to every Airflow job has like an ID, which links to the like code that produced or that was run from that job. And then the artifacts that were produced by that code. And we had to build this system actually internally for ourselves. And I imagine that every startup has to do this. It's not easy.
Got it. Thanks for that.
Yeah. Other questions?
Don't see any other. Oh, there's one on the chat. The targeting. Okay, so it seems like a more general question. We can take that at the end. Okay, let's continue at the top.
Okay. So where was I? Yeah. So I think with all of this, right, if you have a system, doing a forward pass through the system, like creating a prediction is quite easy. But when your client tells you like, hey, your prediction from 2 weeks ago was incorrect, that kind of backtrace is incredibly difficult because even if you know how to trace a forward pass, you don't necessarily know how to trace a backward pass for every single example. And one ML pipeline, right, can involve like retraining and restaging multiple models. So if last week's prediction maybe it might have come from like a different model, in which case, like, how do you quickly go and identify which model is associated with that? And as I mentioned before, every bullet point like has its own tool. So for example, DVC is versioning for data, MLflow is versioning for metrics and model registries. I don't know, I mean, I'm sure there's so many else out there competing with them. And so kind of like, how do you build a stack that has all of these tools? And then furthermore, right, data scientists or ML researchers come from a background in which like they're not using 12, 15 tools like engineers are on a daily basis. And the last thing they want is to add another tool to their stack. So how do you simplify this for a lot of them? It's very hard. Okay. Cool. So I want to also walk through a small example of what happens post-deployment to really like hammer these challenges out there with a simple toy example using this publicly available New York City taxi cab trip data. Like the code is on my GitHub if you want to look at it later in your own time, but for the sake of this, it's not really here. Essentially, this data set is a tabular data set. Each record corresponds to a taxi ride, has the following features like pickup and drop-off times, number of passengers, trip distance, pickup and drop-off location zones, and so forth. It's a pretty large data set, has monthly files from 2009 all the way to like mid 2020. And each month is pretty large, about 100 gigabytes of data total. So kind of, this is pretty similar to, I think, what I experienced. Is like you're working with such large data sets. A lot of the problem here is just to like figure out how to get this data in a bucket and like set up a cluster to kind of just work on this, right? So that's what we did. For this exercise, I guess we'll train and quote like simulate deployment of a model to predict whether a user gave a large tip. And in the tutorial, I use like various Python tools, Dask to work with large data sets. And the goal really here is to demonstrate what can go wrong post-deployment. And I use deployment in quotes because essentially I'll train a model, validate it, and then simulate like what happens if we use this model to do inference on future months, what happens to our performance. And the point here is even if you train and evaluate soundly in an offline setting, okay, soundly is kind of also should be in quotes, but essentially if you follow all the ML best practices that are taught in ML classes, have good training accuracy or training metric, make sure you don't have overfitting, validate this somewhere, you can still run into a lot of problems, I think. And okay, for the sake of the ML part, I might skip all of this, but essentially all we're trying to do is learn some classifier to predict whether a user gave a high tip or not. And a high tip, I define it's like more than 20% of the total fare. And our success criteria here, which is not enough for, I think, staging a model to production, as I'll show. But the criteria here is we hit some sort of baseline metric, maybe like 60% F1 score, and we don't want to overfit. We use a random forest classifier, and super similar to sklearn API. I just copied some of the like basic hyperparameters, but I mean, if you were in industry, presumably you would do a hyperparameter search and have a separate holdout validation set to evaluate that hyperparameter search. But I don't do that here just for time and moving on. Okay, so I train on January 2020 and validate on February 2020. And remember, this is time series data, so you can imagine that it drifts over time. And we simulate like what happens if we send off this model to production and then we use it to do inference on March 2020 onwards. And one fun thing is this is 2020. It's a great example of COVID kind of really hit this month, so we can see the impact of that. We will measure F1 score, which is essentially a combination of precision and recall. And just conceptually, a higher F1 score is better because we want to have low false positives and false negatives. Okay, so come on. Cool. Here's a training code. Essentially, all I do is load the data. I pre-process it, and then I fit a random forest classifier to it with the hyperparameters that I mentioned before. Nothing too crazy, just simple ML stuff. And then evaluating this and getting an F1 score of 66.8%, which is like, if I were in industry, we want to know how that maps to whatever business metric or ROI. But that stuff is ignored here. I don't know anything about taxis. I'm just doing this for the sake of showing ML performance degradation. So imagine we have this, and then we evaluate it on February. Using the same thing, pre-process the February data set, run the inference, and then compute the F1 score. So we can see it's about the same, like literally very, very close to the same, which is great. Good for us. 0.003 difference. We should probably do some more robustness checks or validation checks. I don't know. And this part is also, when I was in industry, I had to like sit and think about, okay, just because I don't have overfitting, and maybe even if this meets a business criteria, does this mean this is good enough? Like, what other things do I check in the data? But imagine that we did this and we're deciding we're ready to deploy on March. I want to mention some caveats with this. It's the, I think I actually mentioned all of this. Yeah, no, it's unclear if the classification problem, it has any business value, but imagine that it does. But let's just move on to deploying this on March. So what does it mean to simulate a deployment? So it's March, we release our model into the world. So one thing that I also nicely ignore in this is like there's a lot of infrastructure challenges around this. So if you remember the like technical diagram that I showed before, we have to somehow figure out how to deploy our model, save it to a model registry, put it in some production pipeline, put it on some pod, and make sure that it's consistently able to be run, especially in an online setting when the data coming in can come in a different format than your data that's in your feature store or in your data lake offline. And another thing is in practice, we might experience data lag where data comes into our databases after some lag. So you could imagine like on February 29th, was it a leave? Yeah, 29th, 2020, we had access to data maybe until February 28th. And that's like in the best case scenario. But in a lot of scenarios, right, you only have access until, you don't even have the most recent month of data or something. Like when I was at my job, one of the prediction problems I had was like predicting whether engines fail. And if an engine fails on the side of the road, it's really only reported to the client, which is like the car company, maybe a month after it gets fixed. And then the car company has to report it to our startup, which could also be some lag. So it's a big challenge to make sure, I guess, the model is up to date, even when you have this lag. For the sake of this tutorial, we're going to imagine that we have no lag, but not always the case. The other thing to keep in mind is when you're doing inference, right? Do you want to do it in a streaming fashion or in batch? And I think that really depends, or a lot of it depends on the business case. So for example, do you need to do inference immediately after every new record? Like for this example case, maybe we could get away with just, I don't know, doing, I have no idea. I think this is really dependent on the business case. In this example, we'll simulate inference on each record as it comes in a stream, but we'll compute the metrics in batch. So what that means is maybe we'll wait for like a whole day's worth of records to come in, and then we'll compute the F1 score and see what happens. Yeah, so in practice, another thing with streaming or batch inference is to consider the infrastructure, like can you support that? And this is a lot of also people collaboration. I had to talk to like infra engineers and PMs to figure out like, okay, what are the business needs and what can our systems do? A lot more collaboration than I would have expected. Okay, any questions?
Questions from the audience, please raise your hand or put it on the chat.
Hi, Shreya. I have a question.
Yeah.
I'm wondering how much portion of these tasks can be actually automated, and what is your take on these auto ML platforms that claim they can automate these stuffs?
I'm not super familiar with auto ML platforms that claim to automate deployment. From what I imagine, auto ML libraries are doing a lot of these like hyperparameter tuning or coming up with the best ML algorithm in training, but correct me if I'm wrong.
Yeah, so I think in the cloud native space, SageMaker has these endpoints and some other plugins that is trying to automate some of this. But typically when they talk about AutoML tools, they don't talk about deployment aspects that much because it's very organization specific. Like Shreya is saying, you have the infrastructure and the environment and the people involved determines what happens. And so the AutoML landscape is too immature to cover deployment, although there's a lot of startups going on.
That's another,
like
somebody may be doing it. I also want to point out with tools like SageMaker or even some of these auto ML platforms, a lot of times when you're building ML models and then improving on them or iterating on them, you end up stacking them or ensembling different methods. Like for example, maybe I have trained a deep learning model and then outputted like hidden layers output is now some feature representation that is now piped to a logistic regression model that is now piped to a random forest, and then that now outputs the thing. I don't know. I've so many startups, like even where I was working at included, like the way that we iterated on the model is just to make it more complex. And then there's the other flip side of the story, which is like the Netflix prize, a famous example of somebody just like won the Netflix prize by ensembling so many state-of-the-art methods, but they couldn't productionize it because it was too complex. And in that case, tools like SageMaker or these kinds of like auto deploy, making it easy to deploy, that's hard, right? What does it mean to deploy such a specific niche ensemble of models? Yeah,
Thank you.
Folks, let's take more questions towards the end. I see a couple of hands. Please keep your questions till the end. Let's continue, Shreya.
Okay, cool. Yeah, so we have no lag here, but just talking about lag in general, we might get different types of lag. One is just feature lag in general, which is maybe our system only learns about the ride and its features well after it has occurred, or even just it takes so much time for the ETL and feature generation to complete. Like some companies have their ETL or feature generation pipelines run once a day or once a week. So in that case, like your lag is just kind of limited or defined by that kind of timing. Another kind of lag is label lag, as I mentioned before. Like for my own company, When an engine broke down on the side of the road, we only learned about it months in advance, even if we got the sensor data tomorrow. So how do you kind of incorporate these different kinds of lag into the same ML pipelines? And I think when dealing with lag, the evaluation metric will also inherently be lagging if you don't have all the up-to-date data. And then that also applies that at training time, your model cannot reflect the most recent period of time. So if I were to train a model, an offline setting, I can't use the most recent data if it's not labeled, or if I can't trust that it's labeled correctly, or I have all of the features. We don't deal with that in this example, but I just want to point out that this is super, super common. Okay, so simulating, quote unquote, the live inference and evaluation. We load up March, we pre-process it, we do inference as usual, and compute the F1 scores. So here I do it a little bit differently. I compute the like F1 monthly score as we did before. And then I also compute daily F1 scores, which means like if I batched all of the data for every day, I compute an F1 score for each day. So the F1 score is similar to the January and February, is this rolling F1 score, which is after every day, what is the F1 score since the beginning of deployment? And then daily F1 is just isolated for that day. And you can see that like, okay, like the performance degradation is not really that much for March 2020 if you look at the rolling F1 score, because imagine the beginning of March, COVID wasn't too big of a problem. So the scores were probably fine. But the daily ones dropped pretty significantly towards the end of the month. And you can see more outputs, I think, in my GitHub, but just to show like really a deeper dive into this, there's this large discrepancy, right, between the rolling metric and daily metric. So one thing is like if you're only monitoring the rolling F1, it might be like mid-April before you learned that there was a pandemic if you were living in a void or something, or that you need to retrain your model. Whereas if you were monitoring a better metric, maybe you could have caught that much earlier on. I don't know. And then this really highlights, right, like data can change. And now the question really becomes like, is there a way to capture that the data has changed? How can we flag that and identify that so that we can retrain the model? And that's like a big question that a lot of practitioners, like myself included, keep asking on our ML tasks. And I mean, just to show that that wasn't like a fluke, right? You can look and evaluate it on successive months like April, May, and June to see that the F1 score does decrease or is significantly different from our 66% that we saw in January, February. Okay, so alluding to this challenge, right, of the data changes, data drifts over time, and inherently models would have to be retrained to reflect such drift. But the challenge then becomes, how often do you retrain the model? When do you retrain a model? And retraining adds this kind of complexity, right, to the overall system, because now all of a sudden there are more artifacts to version, to keep track of. The backtracing, the debugging stuff becomes harder, all of that. Retraining can also be more expensive in terms of compute. So if we're like deploying, I don't know, like transformer models, or just very, very large deep learning models, that can be expensive, both like, I don't know, time-wise and money-wise. And then, of course, right, it's the bottom question is, okay, you know you have to retrain the model at some point. How do you know when to retrain that model? So I'll go through one method that people commonly use to kind of know if the data has drifted. But please interrupt if you have any questions. Are there? I think we're good.
Audience, any questions about this stuff so far? This is getting very interesting. We have a question. Yes, Evan.
So you say like the data changes like all the time, but if you're training like a like computer vision like classification model, like the data like it wouldn't really change all the time, right? Like for the for classification ones on like visual classifications, like
Yeah.
as long as like your initial model is correct, like it should be working for like all the other stuff, right?
Yes and no. One thing that's interesting about research, like vision problems and like canonical NLP tasks, is that those problems inherently don't have like, if you're trying to classify whether something's a panda or not, like maybe that doesn't change too much over time. But a lot of applied ML problems in industry are like recommender systems, ads, predictive maintenance in general. Like you're working with time series data. A lot of it can't. Finance is another great example of this. The news is another great example of this. Yeah, even that's NLP, but you're working with time series data. Every problem in industry, right, can be reduced to some sort of time series problem. And in that case, like it does change. So it does depend on, yeah, the application. But I don't think you will end up going to industry and just be training like panda classifiers regularly or something.
One other thing I would add is even for computer vision, people underestimate how much the drift is a real issue. Like self-driving cars, this is why this is why they're not real. Like why? Because sudden storms and hailstorms and random people running around, these sorts of things are not present even in those vision models training data. It's almost impossible to get the entire universe into the training data of such models. And so they are very brittle in the real world often, and they failed in unexpected ways. And so even for as simple tasks as classification, it can actually fail even in vision. So it's really incredible how this concept drift and this distribution shift problem is so pervasive. Okay, so we have more questions, but maybe we can take one more question. So, and then we can continue. So I see a question on the chat. If the data drifts, would you need to retrain the model on only the new data or the new data and the existing data? In which case would a sampling scheme be needed?
This question is different at different companies and different based on the data scientist who was answering this. I personally like to train models on like, or in offline training, I like to specify the training window that I'm training my model on, training window of time, and then shift that window to validate the process of like the architecture I've chosen and the process of training that I've chosen. So that whenever I need to retrain the model, I just shift that window a little bit once more. But I know some people like to grow their window also over time. It's really unclear to me which one is better. I think for me, all that matters is the consistency in having some process of validating not just the model, but validating the process of training that model, if that makes sense.
Great. Thanks, Shreya. So let's continue and take more questions. I see some more questions. Let's keep that till the end.
Cool. Okay, so I'll talk about this paper called Failing Loudly, Methods to Detect Data Set Shift. And it's nice because they look specifically at tabular data. So essentially what they do is they take two distributions of data, or two data sets, and they want to know, like, are they significantly different from each other? And what they do is they do some form of dimensionality reduction. They run some two-sample statistical test, whether that be like, I don't know, like Jensen-Shannon KL divergence, or like Kolmogorov-Smirnov test is what I'll use in this example. They also use that in the paper. And then they say like, okay, is this statistically significant? And then if so, then we'll just conclude that these are different. So this sounds great, I think, in theory, but let's try to apply it here. One thing to note is that we really only have 11 features. So I will skip the dimensionality reduction step, but they run their experiments on like CFAR and MNIST. So I imagine that they want to do dimensionality reduction there. They also say in the paper that multiple univariate testing seems to offer comparable performance to multivariate testing. So really all this means is we can, for each feature, apply a two-sided statistical test and come up with like a p-value for each feature, and then see kind of what happens from there. And one thing I want to also caveat is I don't want to end up bashing this method. Like, it's very possible that this method does work on like MNIST and CFAR and certain data sets, but for this case, I'll show you that it may or may not work. So a little bit about the KS test. It's essentially, it works on continuous data. And the idea here, I'll go into it in the next slide, is to compute the largest difference between two CDFs. And when I say largest difference, I mean, like imagine we have two distributions here, like this orange one and this blue one. The largest difference occurs whenever X is like, okay, this is up to interpretation. Maybe X is like minus 0.1, like right here, baby, is the largest difference between the two. And the idea is, let's take this difference and we'll call this the test statistic. And let's look at it in comparison maybe to the number of samples, the magnitude of the data, to see whether it's quote unquote statistically significant. And I am not a stats person. I just understood this basically enough to be able to implement or understand why this might be useful and implement this. So anyways, so let's do that. We'll go through each feature. First, let's compare our January and February data sets. And I use like SciPy's implementation of this for each feature. I think one thing to remember is that our January and February are like offline train and test sets had comparable performance, like 66% F1. So we would hope that, or we wouldn't expect things to be very different. So I look at this here, computing the statistic and p-value for each feature. And I print out the table, and what do I find? That our p-values are quite small. And this is interesting. It makes us wonder, like, okay, like, what do we make of this, right? Like, it's saying that basically every feature is statistically significant. What would I do with this information? Are these different, but the metrics were the same? Yeah, lots of open questions there. And one thing to really keep in mind, right, is even though we get low p-values, and maybe this works well when the data has drifted, it can annoyingly flag some sort of drift even when the metric is unchanged, just because there's just so many data points in the sample, if that makes sense. And this is very common, I think, in like this era of big data, right? You just have so many, you have millions, you have here we have hundreds of thousands of data points, right? You can't really look at p-values. They don't tell us anything. And I don't know if I included a slide on comparing January and March, but I essentially got very similar p-values. I should have done that. It's in the notebook in my GitHub. I also got extremely low p-values for that. And it was unclear to me what I could do. And I've also seen this happen. I've tried to do this in industry for my own ML models, and this method is flag distributions is significantly different more than I wanted to do. And I think that's still a very open problem. How do you know when the data has shifted? Like one easy method is maybe I'll just compute the mean and the standard deviation of my distributions and then monitor that over time. But a lot of these like ML problems have data with really long tails, or it might not even be normally distributed, right? So does that even mean anything? Most of these methods have such a high false positive rate that it becomes hard to identify when you actually need to retrain the model. Okay, I will also move on. So I'll move, yeah, so I talked about the challenge in data set shift or drift. There's also a challenge really in establishing more confidence in our training and evaluation pipelines, right? Like clearly we just trained and evaluated offline once and then we deployed it and it wasn't great for us. And especially I think with time series data, there's no use validating just one model. As I mentioned before, you want to validate the process of training and evaluating models. Maybe that means you have rolling train and validation sets. Maybe that means I train on January and evaluate on February. I train on February, evaluate on March. I train on March, evaluate on April, and so forth. And I keep like moving that little sliding window. I would love to see literature on kind of like what is the best approach for doing this. I kind of learned by word of mouth and just working with other data scientists, but it would be really nice to have that rigor somewhere documented. Another thing is really you want to only promote some quote unquote architecture to production if each trained model achieves the acceptance criteria on its corresponding validation set. But in practice, right, this can be very hard. Like what happens if maybe only one rolling validation set didn't achieve the acceptance criteria, but the rest did? Like, okay, do you promote that? I don't know, up to interpretation. And then when you have this like complications, right, like automated retraining and tracing lineage right here it can be very hard to do. Now, all of a sudden your offline training and evaluation pipeline has produced like 12 model binaries. Make sure the right one is promoted to production. Make sure you could trace all of them. Not only does this require, I think, more info work, but also just like, how do you even present the UX of this to a data scientist, right? Data scientists are producing almost hundreds of artifacts on a daily basis. I'm not exaggerating when I say hundreds of artifacts. You could imagine just one of these pipelines could produce a lot. How do you present that in a readable way to a data scientist? Cool. And I think I'm ending my challenges here with collaboration. Not everyone really is trained in, I don't know how to call it, what to call it, I guess ML speak. So for example, right, different people mean different things when they say algorithm. And in general, I think algorithm just means like a series of steps anyone controls, but what does that mean? That means any collaborator controls different things. The data scientist gets to control like the end-to-end training process. So maybe the algorithm for them is the architecture they choose and the optimizer. But for the client, maybe the algorithm is literally everything from they dump something to an API and they get a response. But a lot of that, right, is not in the data scientist's control. So how do you standardize different people's expectations? I think another thing that I realized was very hard is that ML is, well, I know this, we all know this, it's inherently probabilistic, right? Not everything is perfect. Some examples will be classified incorrectly, but we know that we'll get some predictions wrong. We don't know which ones will get wrong. And that's really hard to convey to a client that might not be trained at ML. They don't have, for SaaS, for traditional SaaS products, they're like, it works as intended for everything. What does that mean for ML? Super open question. I still struggle with that on a regular basis. Okay, so I guess hopefully that motivated, I think, a lot of areas for future work. And those are not all the challenges. I just talked about a few. I think even when you introduce deep learning into this, you get many, many more challenges. So for example, if you use deep learning models as intermediate features or embeddings, you have different people maintaining the deep learning models, and you have different people maintaining, like the data scientists that are maintaining the downstream prediction models. If somebody changes an intermediate model, what do all the data scientists do, right? I think in practice, it's very different at different companies. Like for example, at Netflix, they all have like a different fork of their like deep learning models or their embedding models. And each team pretty much like works off, or each even data scientist works off a different fork of the model, which can get quite tedious. And I think from a more like mathematical perspective, for deep learning, right, underspecified, there's a great paper on what underspecified pipelines are and how they can pose threats. So specifically, you can imagine just deep learning models are heavily over-parameterized. So you could have like infinitely many solutions if you were trying to just solve the problem of fitting an over-parameterized model to a specific training set. So as I like, even if you have two different models that achieve the same test set metric, they could have a wildly different live performances, which is really annoying, right, to monitor. And then on the more engineering side and ops side, like tooling here to solve all of these problems is a can of worms. I think my friend did this study of like all the types of tools that exist in ML ops, and I don't know how she had the motivation to go through all of them. Good for her, but there's just way too many tools out there. I'm just fatigued thinking about them. I can't imagine people who aren't fatigued. And I think at the minimum, bottom line, there needs to be some sort of culture shift. And I don't know what exactly that is. Maybe that includes like assigning less hype to fancy models, iterating on the data as much as iterate on the models. And there's so much that we can learn in applied ML from software in terms of how do you incorporate modularity into thinking, how do you do debugging, and etc. So yeah, I think that is mainly it. So I guess hopefully good timing. You can read more of the code on my GitHub, it's there, and then slides are also there. And then feel free to contact me if you have any questions. Yeah, thank you.
Great. Thank you, Shreya. Let's all give Shreya a round of applause, but I am seeing that there is no clap option on this. Oh my goodness. Okay, so I'm going to clap. Thank you, Shreya.
you.
It was a lot of stuff covered and a lot of interesting insights. So now we can take questions from the audience about the talk, and then I will end the recording, and then we can have just a general discussion as well. So questions on the talk? I see hand raised. Yes, Siddharth, go.
How often do you deal with like unsupervised learning or unable data during the process, I guess?
Yeah, there's also application specific. I saw this a lot, but that was mainly because of label lag. Another thing is, even if I get like terabytes of, I don't know, features or sensor data from these vehicles, the labels that come in might be pretty small, or just like we only get a handful of labeled failures. So if we wanted to use all of the data in our training process, we had to do some sort of unsupervised approach. So maybe that meant like train some sort of dimensionality reduction model on the data set, or the large data set, and then use those embeddings to train the downstream like trees on. So it depends, I think, on how, I want to say it depends on how committed you are to solving the problem, whether you want to do unsupervised learning or not.
Got it, thanks.
One question from the chat from before: do people use temporal ensembles of different model versions?
I don't know what a temporal ensemble. Oh, like an ensemble of different versions.
Yes.
I've never asked. I've never done that specifically. I've never asked anyone that question, nor have I heard of that. Okay. Well, okay. I think it depends on what you mean by version. So, for example, maybe I've like trained a deep learning model to do dimensionality reduction upstream, and that is costly to retrain, but that's working fairly well to produce embedding. So maybe I just train another model on top of that. So I guess that would be trained at a different time and have a different version. But it's not like I willingly go out there and find an old version of a model and then stack that under a new version of some other model. I think it just happens as people will just do whatever it takes to end up solving the problem.
Question on the chat. How often, this is a general question, how often do ML engineers read research papers and implement novel ideas in their work?
I did this a lot in the beginning, but I think mainly because I had some sort of FOMO of like, what if I just didn't know what was going on in like deep learning world, because it's really hard. I don't know anyone who keeps track. And then I think as time went on, I want to have the simplest solution to the problem. I actively don't want these complicated deep learning models. I actively don't want these complicated research models. Like I don't want like a student teacher model that I like train, I don't know, some unsupervised model on like 3 million images and then use that to train on ImageNet and then use that in inference. Like I don't want something super complicated. I want the XGBoost model that will work. I want the simplest solution to get from point A to point B as quickly as possible. So from that sense, I try not to use deep learning or just new ML research in the beginning, but personally, I think it's interesting to keep up with papers in fields that I'm interested in. Like I'm very interested in continual learning. I'm interested in adversarial examples, and I'm interested in like just MLSys, stuff like that. But I don't think that's relevant to my job.
Yeah, that's an interesting question. So I've had chats with my ML colleagues about this. Academia and research in industry, their incentives for publications are stacked against what actually works well in practice. And so the systems community, the database community, we understand that simplicity is a virtue. Whereas in the ML algorithmics world, when they want to publish something, you cannot publish us here. We just did a simple algorithm. That's not going to fly. So
It won't, yeah.
there's a mismatch in incentive structures for the ML algorithms like NeurIPS, ICML, and those sorts of conferences. It's fascinating. Let's see how it evolves. One technical question on your content, talk content. So you did say concept drift. I've heard this many times from many people. Concept drift is a huge nightmare for MLOps. How do we tackle this? These statistical methods are oversimplistic. Obviously, they have to be business specific. They have to take into account the variables and which ones are actionable. I've had chats with, I don't know, Mansi Verta. Do you know her? She has this startup in ML deployment called Verta. I've had chats with Alkos Polizotis, TensorFlow Extended at Google. They gave a talk at my DSC 102 last year. And one of the questions I have, which still no one has managed to answer, is how are you going to measure and verify and produce reproducible research on concept drift when people in research and academia in particular don't have access to these real world deployments, these giant fire hoses of model inference results? Do you think people can release logs? How do we even know what concept drift is from an academic research standpoint to be able to verify and validate what works versus what doesn't work?
Yeah, I had thoughts on this. I unfortunately don't have an answer to your question. I wish there were more time series data sets that were canonical in academia, because I think that inherently just brings about these problems. I also think that the DB or the MLSys communities in general can figure out like how we can incorporate logging, and not just logging everything, but a good UX for how people can interact with logs. That I think is the hardest problem. Like how do you incentivize a data scientist to like sit and look through all of the logs that everything, who wants to do that, right? So how do you find the minimal stuff to showcase that like, hey, that something has gone wrong? One other perspective is how do you take the burden away from the practitioner, which is like, how do you empower PMs and how do you empower clients to be able to flag problems? Because they're the ones who will find it first, or whoever's using it will find the problem first. But these people are both like not equipped with the technical expertise to even know that it's a problem, or two, like they don't know how to articulate it.
For the students,
So,
for product managers, I believe, where the ML model is actually helping the product. Okay, follow up on that. This whole space of feature stores, ML platforms, I've been teaching this in my graduate, again, plug for the students, CSC 234, data systems for ML. I offered in the fall. I talk about this, and Mate came and gave a talk last fall about ML flow and stuff. I'm a big fan of ML flow. It's been a very big success. One question I have is, what about standardization in this space? What defines an ML platform? What defines a feature store? And again, coming back to this question about benchmarks, how do we know that it's good? How do we know that it's not good? How do we improve? What's your take on this?
Yeah. Okay. So how do you standardize infra for ML?
Their own feature store. They're building their own platforms. You pointed out Uber. There's like a dozen others that I talk about in my class too.
Yeah.
And everybody's building their own tooling. And in the 80s, this happened with relational DBMSs. And then people started benchmarks, and then they understood what is a canonical architecture. And then consolidation happened. Do you think this will happen in the ML platform?
Oh, 100%. But I think the problem right now is, okay, I was not alive in the 80s, so I don't know I just have read the history of like relational databases. But I think one problem in this space right now are people who are like the 12 ML ops companies that are probably building feature stores or whatever, is that people are trying to solve the immediate problems of today without having like a vision of how these future stores will be used in the future. Like, I really want to work on feature stores, for example, like in the future. And I think like the way to do it is to think about like, okay, like we are all trying to move towards online learning and industry. So like, how do you fundamentally build like some sort of like middleware, I want to say, from ETL to data science, in an online learning setting, and treating it as that rather than like solving the problem of data scientists working off of different versions of features. Because I think that's how a lot of current feature store people are trying to simplify the problem. Whereas then it becomes like this like patching like problem instead of building the right abstraction for everybody.
That's how development becomes research. We understand in systems world, we learn from the practitioners and then we abstract it and then it becomes research. Okay, so one more question and then we can move to the discussion, open discussion. What do you think about the future of job titles in this space? ML engineer and data scientist seem like catch-alls to me. So in the history of computer science, there is no title called computer scientist. So there is software engineer, software development engineer, software test engineer, security engineer, network engineer, database engineer, database administrator, so many things. Do you think this whole space of ML systems will also fragment into specialized job titles over time? ML engineer, ML test engineer, ML UX engineer, ML security engineer, data engineer and data scientist will probably still be around.
I feel like I haven't been alive for long enough to be able to make a conclusion on this.
The industry,
yes and no. I don't think it matters, to be completely honest. The skill sets will all be needed.
Okay.
And I think the software problem, like from an industry perspective of hiring, has never been great. I don't think it will standardize magically and become great, especially for ML. The only thing, it'll become worse and more fragmented. But at the end of the day, right, these skills will not go away. So I would not worry too much.
Sounds good. So that means you need to have a principal foundation in this whole space. And
yeah.
I'm talking to the students, so that's part of the reason why UCSD invested in data science so much, and that's why we have HDSI. So that's awesome. With that, let's wrap the recorded portion of this. Thank you again, Shreya, for coming and giving the talk and answering the questions. I will stop the recording now.